this point. So welcome everyone to RASC Halifax Center's monthly members meeting. I'm Judy Black, the president of the center for this coming year. Welcome everyone. We have a mixed bag of guests today. Not only do we have our own Halifax Center members joining us, but there are also many from far afield. So welcome all. The agenda for today, and I'm going to share my screen at this point. There we go. Is after the welcome, Paul Gray will be providing our photo montage. This is a collection of photos and sketches over the past month, although I guess Paul will actually be the last couple of months. We have some special announcements to make that no one except executive knew about this, so it'll be a surprise for everybody. We have two special guests this month. We have Dr. Luigi Gallo from St. Mary's University to talk about black holes, the loud, the quiet, and the silent. And we also have Michael Gatto talking about his sketching and digitizing images of Mars. If you looked at the Journal of the RASC, you'll see Michael's sketches on the back cover of the latest edition. We also have Paul Heath with his Food for the Soul, and that's the wrong title of the poem, and I apologize for that, Paul. What's Up in the March Skies will be presented by Dave Chapman, and then I will give you news from the board. That is the end of the official part of the meeting, at which point the recording will be stopped, and any member that would and guest that would like to join us for an Astro Chat afterward is free to do so. And please note that it is not recorded. It's totally just a bunch of people getting together to chat about anything and everything. So you're welcome to join us. So Paul, I'm going to stop sharing. Are you ready for the photo montage?
Find my mute button there. Yes, Judy, I think I am. Let me just get it up and running and try and share this thing. Interesting. There we go. All right. Yeah, I mentioned last month we didn't have much in January because the weather was crappy. I don't know about everyone who's visiting from the rest of the country, but down here it's been really bad. And February was actually a little better. A number of people got out. We've got a bunch of photos from sketches. I wouldn't say a whole lot, but more than we had for the rest of the winter, I think. So I'm not going to say a whole lot about them. Just going to let them play through. I think there's a dozen in here this time. Weather is improving, getting a few clear nights. I haven't had much luck here on my side of the province, but obviously people have been getting out and seeing some stuff. Dave Chapman was up way too early. A few people were actually. Blair's done some great work from the driveway. Yeah, in Bedford. I don't know how he does it, but he does a good job with his deep sky stuff. Peter got lucky with this grab. I don't know how he timed it, but just a fluke. Nice to see people taking advantage of the clear skies even under the moon and twilight and when things aren't always great. David's been doing a good job with his moon shots. Images are getting better all the time. February, March are great times to see the belt of Venus. A few members have seen it. I've witnessed it a couple times. I never photoed it. Again, Blair and his backyard setup. I think this is really impressive. David Hoskin with Uranus and 4 of its moons. That's a pretty impressive shot for a backyard telescope. It's amazing what we can do these days. Mike Bosch shot shooting from his apartment windows in Halifax again. Get some amazing views down there. I'm not sure how many people saw that morning, but it was a beautiful morning and a pretty sight. That's it.
Wonderful. Okay, we have two special announcements to make this morning or this afternoon, I guess, depending what part of the country you're in. One of them has to do with a recent member to us who has, in terms of, he has been a member of Regina Center for many years, but recently came to us about a month ago. And it's no surprise, James Edgar from Saskatchewan was nominated by what would be now 5 fellow members of the RASC, members of the Fellows of the RASC. Roy Bishop, Dave Chapman, Pat Kelly, Dave Lane, and Mary Lou Whitehorn, who nominated him. And he joined the RASC in 2000. He started with the Observer's Handbook back in 2001 to 2005 as a proofreader, was the assistant editor from 2005 to 2016, and he was the editor from 2016 to now. And I believe you've signed on for another 5 years, James, is that correct?
That is correct, yes.
There you go. Congratulations on that. He has been, he was a proofreader for the Journal of the RASC, but he's been the production manager since 2006. That means 89 issues of the Journal of the RASC he's overseen. He was a member on the National Board of Directors from 2007 to 2016, and actually served as its president for a couple of terms. And one of his sidelines that he does that combines his love of woodcrafting along with astronomy was he has some astronomical wood carvings at the CNIB offices. So quite interesting there. He also received 2 other awards, Simon Newcomb Award in 2009 and the Service Award recipient in 2012. So James, congratulations.
Thank you.
On your well-deserved award. And I love the quote from your nomination that said, "The involved, exceptionally capable, affable, retired locomotive engineer from the prairies." So congratulations and a formal welcome to Halifax Center as well.
Thank you. Happy to be here.
Now, the other nomination that we have, this person doesn't know about it. They were nominated by myself, Roy Bishop, Dave Chapman, Mary Lou Whitehorn, and Paul Heath. And and I'm sure he's going to guess who it is, and it is a he. He joined the RASC 30 years ago. He has served on Halifax, what was then called the Council. He served as the Nova East Star Party chair from 2012 to 2014, and he has adjudicated the Astro Imaging contest here since its inception as a center's contest in 2017. He's done presentations here in Halifax at Nova East and certainly in virtual observing sessions. He's done articles in Nova Notes, in the Journal of the RASC, as well as the Observer's Calendar. He is a recipient of the Burt Gaffney Award for Writing and Publishing. And this is the dead giveaway. And if he doesn't guess it's him, I'm surprised. He was one of the founding members of the RASC Astro Imaging Committee back in 2015. And he is a mentor extraordinaire to Halifax Center Astro Imagers. So I would like to offer congratulations as being a recipient of the RASC Halifax Service Award to Blair McDonald. So yay, Blair.
Thank you very much.
This is why I was trying to convince you to come to the meeting today.
You didn't have to convince much.
That's good. That's good.
Thank you very much, everybody.
So you're more than welcome and more than deserving, both of you. Okay, now we come to our special presentations. Our first up is Dr. Luigi Gallo. Luigi is a professor at St. Mary's University in the Department of Astronomy and Physics and has been there since 2007. He received his PhD for work conducted at the Max Planck Institute in Germany, and he's worked in Europe, Japan, and the US. And he was the Canadian lead on the Canadian Space Agency contribution to the international JAXA-led Hitomi X-ray mission. And I believe you presented on that way back when, Luigi, to our center. And he's now the Canadian lead on the JAXA NASA-led, is it XRISM?
Prism.
Yeah, it's spelled XRISM, X-ray mission that will launch in 2022. And most of Luigi's research has focused on high energy emissions from black holes. And today his topic is black holes, the loud, the quiet, the silent. Sounds like a family gathering. So I'll let you take it from here, Luigi. Thank you.
Thank you very much. Let me see if I can share my screen here. There we go, should be in presentation mode. So thank you very much for having me. I always enjoy coming to spend time with you guys. It's a lot nicer to do it in person, but unfortunately this is where we are right now. So that's fine, we'll make do with it. I was, yeah, so as Judy was saying, the last time I was with you guys was a couple years ago, and I talked about Astro H, or Hitomi. We have Chrism, which is coming up in a couple more years. So hopefully I'll have an opportunity to come visit you guys again and talk about that when it comes up. When Judy contacted me, she said if I would be willing to talk about my research. So of course, as a scientist, I was ecstatic about this because, you know, you give us a platform to talk about the work that we do. We're totally going to jump on it. As a father of 2 teenagers, the fact that anybody wants to hear anything I have to say is actually really exciting. So I'm definitely going to take advantage of it. So I'm going to talk about black holes. I'm going to talk about my research. I'm actually going to leave that to the end. There have been a lot of real massive discoveries and very high impact results that have come out of black hole research over the past couple decades. And I want to focus on some of those before I actually talk about my work. First thing to do is probably explain my title a little bit, the loud, the quiet, and the silent. Obviously, we don't hear black holes. We're not listening to them. I think when I came up with this title, I think I was more thinking in terms of personalities as opposed to something to do with volume. The loud black holes are kind of obvious. Okay, so these are we also call them active galaxies or X-ray binaries. This is an example of an active galaxy. You see the fuzzy region there. That's the host galaxy. That's the galaxy. You guys have all taken pretty images of this. This is 100 billion stars gravitationally bound together. But you see that the very central region, there is something that completely outshines the entire galaxy. Okay, so this region is tiny. It's the central supermassive black hole, and I'll talk about that. So this is an example of your loud neighbor on the street. You definitely know he's there, okay? He's only occupying one little house over the whole block, but they stand out, right? Here's another example of a loud neighbor. This is the black hole in the galaxy Cygnus A. So here's your host galaxy of 100 billion stars again, but this black hole is now ejecting material in this collimated jets, which extend out to these giant plumes of material. This is ejecting material is reaching out to about 300,000 light years across. Okay, so a light year being the distance that light travels in 1 year. This is 300,000 light years across. So this is not only affecting the neighborhood, this is actually affecting other galaxies. So this is another example of a very loud black hole. This one is one of my favorite black holes. This is IRAS 13224. This is the most technical plot I'm going to show you, I hope. This is the brightness on the y-axis over here as a function of time. Now, each one of these gray bands is about 1 day in duration. And this is how the brightness is changing over that period of time. So over the period of a day, the brightness will change by about a factor of 10 to 50, just rapidly going up and down over the period of a day. Okay, so when you do the calculation, you figure out that that's equivalent to about 100 billion stars, which are turning on and off. So if you can imagine, you remember how annoying it is to have your kid in there flicking on and off the living room light. Okay, now imagine the entire galaxy, including the sun, is going on and off over the period of hours. Okay, so this is not a loud neighbor. This is an obnoxious neighbor, right? I mean, this is obviously something that you notice. So these are the kind of galaxies I look at, are these loud ones. These loud black holes are the ones I work. So I guess similar characteristics, similar personalities, I suppose, attract each other. So I'm going to get back to these guys, but I kind of want to move on and talk about the other types of black holes. First thing I need to do is I need to explain what a black hole is. So what is a black hole? The definition of a black hole is actually kind of ingrained in Einstein's description of general relativity. So that's the equation, that's Einstein's field equation. I'm not going to dwell on it. Don't hang up yet. So this is a very simple looking equation, very complicated in nature, but it basically describes general relativity. This is general relativity field equation. What this is basically just geometry. All right. So we know, you remember the distance between the shortest distance between 2 points is a straight line. Okay. That's not necessarily the case when you get into the universe, when you get out into space, right? I mean, even on the surface of the Earth, the shortest distance between 2 points on the Earth over the surface of the Earth is actually an arc, right? So, and when we get out to space, it just becomes even more complicated. So it's just geometry. That's all general relativity really is. But what Einstein did, one of the fallouts of this is that black holes are a consequence of general relativity. And this was actually a discovery made by Roger Penrose, and he won the Nobel Prize in 2022, just a few months ago, in October 2022, he won the Nobel Prize for this discovery. So this theoretical foundation that black holes have to exist if we believe that relativity describes the geometry of the universe. Okay, so there is theoretical foundation for this. That's not entirely useful for astrophysics. All right, for the kind of stuff that we're doing here, we're not really worried about the equations per se. So if you ask me what a black hole is, I'm going to give you a slightly different answer. It might still sound complicated, but let me try to explain it. Okay, I would say that a black hole is a region of space containing so much mass that not even light can escape its gravitational pull. Okay, so you imagine we're gravitationally attracted to the Earth, right? We're walking around on the surface of the Earth. We can jump up and down, but there's no way that we're going to escape the gravitational pull of the Earth. However, if we turn on a flashlight or a laser pointer pointed up to the sky, that light is going to disappear. That light is going to escape without any problem. All right. So we're talking about something where the gravitational pull is so strong that not even light would be able to escape that gravitational pull. Okay. So mathematically, what Penrose was talking about and Einstein are talking about is that all the mass within a black hole is contained in a single point of space called the singularity. All right. We don't even come anywhere close to this in astrophysics. All right. For us, what's important is the definition of the event horizon. This is a boundary around that singularity that defines a region of space where nothing can escape from it. So if I'm standing inside the event horizon and I shine my laser pointer, the light is going to eventually fall into the singularity. If I'm standing outside the event horizon and I shine my laser pointer, that light, I have to work pretty hard, but it's going to escape. Okay. So from within the event horizon, we see absolutely nothing. Okay. So that's what makes it black. That's why we call it a black hole. The parameter that defines, there's only one parameter that defines the size of the event horizon. That's called the Schwarzschild radius. And the Schwarzschild radius depends on only one parameter, only one property, the mass of the black hole. How much mass is contained in that singularity? So the more mass you have, the bigger the event horizon. The more mass you have, the bigger the black hole. Okay. So what's interesting about these definitions or what we're calling here is that there's nothing special about the black hole. Anything can be a black hole. If you can take any kind of material and squish it down, somehow you can put enough pressure on it that you squish it down to its Schwarzschild radius, then it will become a black hole. So the Earth, for example, 13,000 kilometers across, has a radius of 6,500 kilometers. If you want to squish that down to a black hole, you have to squish it down to a radius of 1 centimeter, basically the size of a marble. Okay, so if I'm standing on the Earth, shining my light, it's going to escape. If that Earth somehow squishes down to a radius of 1 centimeter and I'm still managing to stand on it for some reason, the light is going to get trapped in it. Okay, so a black hole the size of the Earth would be 1 centimeter in radius, 2 centimeters across. The sun is 110 Earth diameters, okay, or 300,000 times more massive. If we could squish the sun down to the size of the Halifax Peninsula, a radius of 3 kilometers, the sun would become a black hole. All right. So anything, if you can take anything and squish it down to a small enough radius, it will become a black hole. So what do we know that could actually create black holes? Obviously, you can't imagine that we could actually create enough pressure that we could squish something so small that it would become a black hole. Well, the one way we know how to make black holes is through stellar evolution. All right. And this isn't stellar evolution of a sun like ours. This is a very massive star on the order of 40 times more massive than the sun. You take a star like that, as it runs out of fuel, what happens is that the core of the star starts to collapse on itself. There's nothing can support it anymore because it's run out of fuel and it starts to collapse on itself. The outer regions are going to have this violent explosion we call a hypernova, even more energetic than a supernova. So the outer region is just going to explode and go off into space. That core keeps shrinking and shrinking and shrinking and falling in on itself until it falls within its own event horizon and it becomes a black hole. Okay, so what's left after all this explosive material disappears is the very core of that star, which is about 10 solar masses in size, and it's a black hole. Now, I've already showed you pictures of supermassive black holes, ones that are millions or even billions of times more massive than the sun. How do we make those? We still don't have a complete picture. We still don't understand that completely. I'm going to talk about that a bit later. But what we do know is how to make black holes that are 10 solar masses. All right. So great. We'll get back to the size thing. For now, I kind of want to think about how do we find black holes? It's easy when they're loud. It's easy when they're active. It's easy when they're obnoxious. They stand out, quite simple, right? But what if they're not really interacting with their surroundings that much? Okay. What if this is your quiet neighbor now? Okay. What if he's the person down the block who, nice enough, and he'll wave at you every time you walk by. You might have a short conversation about the weather when you walk by, but doesn't really, kind of minds his own business, doesn't do much else. Okay. Well, how do you find those guys? How do they stand out? Okay. And it's really complicated when you think about the size of the neighborhood. Okay. Now I talk about a supermassive black hole that's 1,000,000 times more massive than the sun. Sounds big, sounds impressive, but keep in mind that a galaxy is 100 billion times more massive than the sun. So it's the black hole, as big as it is, it's still tiny in comparison. So how do you find that? One of the quiet black holes that we know about is at the center of our very own galaxy. So at the very center of the Milky Way is a black hole called Sagittarius A star. Now, if you've had an opportunity to go south of the equator and very dark skies, this is an image taken from the Very Large Telescope Array in Paranal in Chile. And just a beautiful scenery here. That laser, I'll explain what that laser is in a second. That's actually pointing to the center of our galaxy where we know Sagittarius A star is. Okay, but I just want to point out the galaxy. So what we're looking at here is the plane of the Milky Way, the edge of the Milky Way. All right, and you see that it's all this light. This swath of light is actually they're actually stars. Each one of those is a pinpoint of starlight. There are so many stars, so much stellar material, all very close together that it just looks like it just looks like a bright swath of light. All right, but it is actually stars, individual stars. We can't make them out. Another thing to point out is these dark patches. That isn't places, those aren't regions without stars. There's just as many stars in these dark patches as there are in this big swath of bright light. But that region, there is a lot of gas and dust between us and the and Sagittarius A star, so we can't see the stars behind it. All right. So the first challenge when we want to look at the center of our galaxy is that we have to look at a wavelength that we can penetrate through the dust. So we make these observations in infrared wavelengths. All right. So that's the first thing that we're doing, is looking at the infrared. The next thing that we need to worry about, because these telescopes, these giant telescopes looking at infrared, they're located on the ground, right? So we're making our observations through the atmosphere, and you guys know better than anyone how difficult that is, right? So the atmosphere is very turbulent. It's effectively, it's a fluid. It's like as if you're standing in a lake knee deep, and you look down and you can see rocks at the bottom, but basically the image of the rock kind of changes and the sharpness kind of fades in and out and so forth, because the water is moving around. Same thing is happening with the Earth. All right. So the atmosphere of the Earth is moving around, it's turbulent, and it's going to make your stars twinkle, right? And that's not a good thing. Stars don't twinkle because they, by any physical nature, it's simply an effect of our atmosphere. So we need to correct for that to make very sharp images. And the way we do that at this observatory is through a process called adaptive optics. So what happens is a laser of light is shot up into the sky, and that's what you're seeing in the background there, that image of that laser that went up into the sky out of the telescope. So you're going to make an observation of your star and the laser light at the same time. Now we know what the laser light is supposed to look like because we are the ones that shot it up into space. So when it comes back down, when the reflection comes back down and we take an image of that in our telescope, we see that it's been distorted because of the atmosphere. So we know how to correct for that, or if we could correct for that, we can then produce a sharper image. We have a deformable mirror, and what this is basically a mirror which just kind of very slightly changes its shape so that it can, in real time, so that it can actually correct for the distorted light coming. So you can make these corrections, produce a very sharp laser image. In doing the same correction to the star, you produce a sharp star image. All right, so that's the process behind this, and it's called adaptive optics. And these are the effects that we're seeing here. This is without the adaptive optics, and this is with adaptive optics. And you see the difference, right? And I'm just going to point out the size scales here, hopefully impress you a bit. The big square on the left, I don't know if you guys can see my mouse, but the big square is 6 arc seconds, and the little square is 1 arc second. So an arc second, your finger held out at arm's length, the width of your fingertip is 3,600 arc seconds. All right, so imagine taking your finger width and dividing that into 3,600 parts. That's how big that little square is. Okay, and you can see the sharp images. So looking at Sagittarius A star, within 1 arc second of it, we're seeing all these stars located in very close region. It gets better. This is a really cool part here. This is an image within that 1 arc minutes. Okay, this is actually real. These are actually real images. These are all stars. Okay, they've just been color coded, and we could talk about that after. They're just color coded in a specific way. And what I'm going to show you is this image, the same field. They've taken continuous images for about 25 years. So if in the top right, you can see the date, 1995 is when it starts. It's going to run up to 2020. Okay, so I just want to show you what these stars are doing. Okay, so we can actually see the stars moving in this region. And what's fascinating is all the stars seem to be moving around a point. That 5-pointed star there at the very center. That's the very center of the galaxy. That's where Sagittarius A star is. So all these stars are moving around this common point, Sagittarius A star. This is our favorite star. This is S2. The reason we like it so much is that in the 25 years that we've observed it, it's actually completed a couple of orbits. And what's fascinating about the orbit is this special shape that it makes, an ellipse, right? And if you've taken your first year astronomy course, you recognize the ellipse as being a very important shape when we're studying orbits. All right, so there's a couple things that we can look at. This is the ellipse itself, okay, from that star S2. That 5-pointed star is the location of the center of the galaxy where Sagittarius A star is. And we find that we look at it on the right, bottom right, if you see my mouse there, that point is called the focus of the ellipse. All right, the distance between the focus and the closest approach of the star is on the order of 40 astronomical units. An astronomical unit is the average distance between the sun and the earth, okay? 40 astronomical units is the distance to Pluto, all right? So that is actually fairly small, big number for us, but astronomically speaking, it's tiny, okay? So this distance between Sagittarius A star and the closest approach tells us that this region of space is smaller than the solar system, okay? But we can use Kepler's laws now, and this is what you would learn in first year astronomy. You use Kepler's laws, and you can actually calculate the mass located at Sagittarius A star. And we find that Sagittarius A star is a supermassive black hole that has a mass of 3.5 million times that of the sun. And for this discovery, Andrea Ghez and Reinhard Genzel won the Nobel Prize in 2020, back in October. So a very new discovery. These are two independent groups. And Andrea Ghez is at University of California, and Reinhard Genzel. I'm going to do some name dropping now. Reinhard Genzel is at Max Planck Institute, where I got my PhD. I actually took the course on Sagittarius A star, the center of the galaxy, from him. So yeah, okay, so drop the mic kind of thing here. So very massive. This is over 30 years of work that went into this. So quite phenomenal result for the discovery of the supermassive black hole at the center of our galaxy. All right. All right. So that's a quiet neighbor. One that's not so active, but it's still leaving an impact. Okay. One of the questions that we often get is, look, why can't we just take pictures of black holes? All right. And this is actually very complicated. We did take a picture of a black hole. The very first picture of a black hole was published a year ago, and I'm going to talk about that result now. But the first question I'm going to answer, or try to answer, is why is it so hard? Okay. And the issue is, it isn't so much collecting area. It isn't so much that we don't have telescopes that are big enough to see that region, but the issue is actually resolution. Okay. Now, resolution is the ability to distinguish two nearby points. Okay. And identify them as being separate points. So you're waiting at the bus stop, you look down the street and you see lights coming towards you. You see, it looks like one big light, right? You can't tell if that's a motorcycle with just one headlight, or if it's a car with two headlights, or if it's a bus with multiple headlights, right? So it's coming towards you. As it gets closer and closer and closer, you start to distinguish that it's two headlights and it's actually a car, not a motorcycle. And of course, it's not going to be your bus. You still have to wait another 20 minutes for your bus. Okay, so that's what resolution is, being able to distinguish those fine points. And this is something that depends strictly on the size of the telescope. The bigger the telescope, the better you are, the better resolution you can achieve. Okay, so this is part of the challenge. We can only build telescopes so big. You can't just build an arbitrarily big telescope. But what we can do is we can create interferometers, all right? And this is a technique that takes multiple telescopes, links them together in order to improve the resolution. We're not necessarily collecting more light, but we are improving the resolution. And the way this works is basically you take two telescopes on the left-hand side, you take two telescopes. If you time the signal, when the arrival time of the signal is, and you can kind of connect that, you can use it to achieve the resolution as if you had a single telescope with a diameter equivalent to the distance between each one of these telescopes. Okay, and this is something that we can do really well in radio astronomy. This is one of the longest working arrays. This is the very large array in New Mexico. This is where Jodie Foster in Contact made, got the signal from the aliens, who ended up being her dad. But this is taking 27 telescopes. Each one of these telescopes, radio telescopes, is about 25 meters in diameter. But when they're linked together, they act as if they're a single telescope that's about 21 kilometers apart. All right, we can't build a single telescope that's 21 kilometers, but we can use multiple telescopes together to try and achieve that kind of resolution. All right, so that's where we are now. Now, if we want to observe the next trick, if we want to observe the biggest black holes, they're the ones that are going to create the biggest image, right? We either have to look at the nearest black holes like Sagittarius A star, or the very biggest black holes that are as close as possible. So there are two candidates that stand out, Sagittarius A star itself and M87 in the Virgo constellation. All right, so that's the biggest black hole that's nearby. In order to get an image, make an image of those, we would need a telescope that's as big as the Earth. Obviously, we can't build a telescope as big as the Earth, but we can connect a bunch of individual telescopes to do that. And that's what's called the Event Horizon Telescope. Depending on the configuration, the Event Horizon Telescope uses about a dozen different observatories and makes an observation simultaneously in order to try and improve resolution. And back in April 2017, they did that. They observed M87 in this kind of configuration with as many telescopes as they had. I think they had over 6. I can't remember exactly the number of telescopes that participated in it. But they created an image of M87. Before I show you the image, I think it's kind of important to say, what do we expect it to look like, right? Because I mean, like, if we don't know what a black hole looks like and we just take a picture, then, you know, and I show it to you, it's like, okay, well, maybe that's a black hole. I don't know what a black hole is supposed to look like. Okay, so what do we expect a black hole to look like? And this is going back to what those field equations and Penrose idea. Basically, the idea of the geometry around astronomical objects. So everything with mass, whether it's the Earth, the sun, neutron stars, or black holes, or galaxies, will create some curvature in space-time. The bigger the mass, the more curvature is created. All right. So what this means is that, like moving along the surface of the Earth, that light is not traveling in a straight line. And well, what appears to be a straight line to us, it's actually going to be curved. So in principle, we should be able to see, in an idea like this, we should be able to see light, which is actually behind the black hole coming up. All right. So this is what we think might happen. If you imagine on the right-hand side what we have, this is kind of the black hole itself. What we're seeing edge on is a razor-thin disk of material, okay, which is swirling around the black hole. Above and below it, we are actually able to see the light from behind the black hole curving up behind it, from behind it, curving up and coming into our line of sight. All right, so we expect to see something that's kind of spherical like that, or circular like this, right? We also expect to see one side of the material to be brighter than the other side. This is due to beaming effects. Things that are moving towards us are going to appear brighter. Okay, so this is kind of what we think. And then you can imagine that if you change the inclination, you're going to get different manifestations of this, right? This is the very first image of a black hole taken 2 years ago. All right, this is M87. And just to point out some sizes here, it was published in 2019, but the data was taken in 2017, I believe. This is as close as sharp an image as we can get of a black hole to date. All right, and just to point out, 300 astronomical units away, in size is basically where this bright band is. We see a region, we see this kind of circular shape. We see a region of it that's brighter, that stuff is coming towards us, compared to a region of it that's moving away from us. So that beaming effect, just like was predicted by Einstein and Penrose and so forth. All right. The name Event Horizon is a bit of a misnomer here. There is the event horizon itself. I just kind of drew it in as a dotted line. We can't see it directly because we're kind of in the shadow of the black hole itself. Okay. So that's the very first image of a black hole. We're working on, we astronomers are working on doing the same for Sagittarius A star. Bit more complicated for Sagittarius A star because it's actually a bit louder. It's actually a bit variable, so it actually changes its brightness. So it becomes more difficult to take the image. But hopefully this opens up a new area of research for us. All right, so we've talked about the loud ones, we've talked about the quiet ones. What about the silent black holes? What about your hermit neighbor? You know, the one that you walk by and you don't even know if anybody lives there. The grass is cut, but you actually never see anybody. The lights are never on. You don't even know if they're there or not, to be sure, but it definitely looks like somebody should be living there. How do we see black holes that are not interacting with their surroundings? Backing up, most black holes are like this. Most black holes are not interacting with their surroundings, and most black holes in the universe we don't know about. So how do we see these? Okay, we go back to Einstein's equations there. All right, what I talked about, curvature of space, you have a big mass that's sitting in space-time. It's going to create curvature and light goes around it. But there's one more catch here. if you have that big mass which is now moving, whether it's spinning around or if it's moving in space, it's actually going to create ripples. Not only is it going to create this big divot where everything is bent around it, but it's actually going to create ripples, kind of like dropping a stone in a pond creates a ripple, right? Now everything in space is moving and everything in space is spinning. Everything is creating these ripples. So imagine standing in the middle in your boat, of course, in the middle of the pond, and there's stones and everything moving around and it's all splashing. There's ripples all over the place. These ripples are called gravitational waves. And we've just kind of entered in the realm where we can actually detect these gravitational waves, all right? The biggest ripples are created when black holes collide together, all right? So even if you're in the middle of the pond and you see all these ripples going around, if a speedboat comes by, you're going to recognize that those ripples kind of stand out above every other ripple, all right? So those are the ones that we're actually looking for in this. How do these work? This is the observatory, which actually made the very first discovery of a gravitational wave. This is the LIGO Observatory, Laser Interferometer Gravitational Wave Observatory, all right? And the way this works, it's not a telescope. It doesn't use optics. It's not giving off light. We can't see the light from this system, right? What happens here is you have a laser, a detector. I hope you guys can see my mouse moving there. And you have two mirrors located at the end of these 4-kilometer arms, okay? So laser is shot out. It goes through a beam splitter, which just means that it's going off in 2 different directions. And it travels a length of 4 meters and comes back another 4 meters. So each one of these beams goes, the beam goes out a total travel distance of 8 kilometers, right? And it comes back, it comes together, comes back to point B where it merges, and then it moves over to the right where it gets detected on your detector. When the beams go out, they're the exact same beam, but they go out just out of phase. So what happens is that when they come back, if everything's perfect, and they've traveled the exact same distance, they've traveled exactly 4 kilometers both ways, and they come back and nothing unusual is happening, they're going to be just out of phase where they kind of cancel each other out. So the detector should see nothing, okay? So that's the principle behind the Michelson interferometer here. Shoot a laser, goes off just exactly out of phase where when it comes back, you get 0 detection. The light basically cancels itself out, all right? So think about the waves on a pond. You have peaks, you have troughs, and when the peak and a trough kind of meet each other, it just cancels itself out, right? So you shouldn't get any waves at that point. That's what's happening with the light here, okay? But now imagine that you actually have a ripple in the space-time. So now what's happening is that there's a wave on the surface of the water, okay? So imagine a leaf moving on that surface of the pond, but now it's moving in the wave. Well, the actual distance that it moves actually changes depending on this wave, all right? So this is going to change the path length that one laser beam going to the left versus the one going to the right. It's going to slightly change the path length that those travel, such that when they come back and meet, they are no longer exactly out of phase, so you actually see the light, all right? And that's a detection of a gravitational wave. So there's an observatory. This is LIGO. This is the observatory that made the first detection. It's actually 2 identical instruments. You get 2 laser with the beams that are 4 kilometers apart. There's one in Hanford, Montana, I believe. Correct me if I'm wrong. And the other one's in Livingston, Louisiana. Okay, so they're separated by 3,000 kilometers. And you can imagine if there's a gravitational wave that comes in from the left, it's going to hit Hanford first, and then 7 milliseconds later, it's going to come into Livingston. So
I think Hannaford's in Washington State.
Washington, thank you. I'm sure I would have upset somebody if I said that in the States. So then 7 milliseconds later, it's detected in Livingston, all right? So exactly light travel time between the 2 points. All right, so this is done for redundancy so that they can get a detection at both places at the same time and compare the signal. And in September 2015, this is what happened. This was the first detection. And you see how this is the signal from Hanford. And you see that you get this kind of like just these slight oscillation, and then it gets stronger and stronger until the oscillation, the power of the oscillation kind of peaks. And then it goes off to being kind of dismissing again. All right. And what this is interpreted as is two black holes that are coming closer and closer together. And as they come closer and closer, the ripples start getting stronger and stronger, and they peak just when the black holes crash together to form one or bigger black hole. And after that collision is over, it goes back to being quiet again. Right? So this was the very first discovery of a gravitational wave, and what it was seen as is two black holes on the order of 29 and 36 solar masses coming together to form another black hole, a single black hole of 62 solar masses. All right. And for this, Wise, Thorne, and Barish won the Nobel Prize in 2017 for the detection of gravitational waves. So this obviously opens up a brand new area of study where we're not just looking for light, but we can actually detect, now we can actually detect gravitational waves. So we're entering in a realm of multi-messenger astronomy, where it's not just light that we're looking at, but we're looking at other forms of radiation. Okay. This brings me back to one of the first points I made about how do black holes grow. Okay, so we know that we have supermassive black holes, but we know how to make black holes that are about 10 solar masses. So how do we get ones that are so big? And this does look like we're now actually discovering black holes that are hundreds of solar masses, which are coming from the mergers of smaller black holes. So smaller black holes colliding together, forming bigger and bigger black holes, right? Where you can't, with LIGO, we can't actually go and start looking at those supermassive black holes. We can't see the collision between supermassive black holes because the frequency of those oscillations is slightly different. You need a much longer arm for your laser. So in order to see that, we're actually going to have to wait till 2034 for a mission called LISA, the Laser Interferometry Space Antenna. And this is going to be launched. It's a European Space Agency mission. It's being launched in a solar orbit following the Earth. There's the Earth there with the moon. These lasers are going to be separated by 2.5 million kilometers. And with that, we should be able to detect, we are going to be able to detect gravitational waves, which are coming from the collision of supermassive black holes together. Okay. So the next step in multi-messenger astronomy. All right. I want to go back to the loud black holes. So we talked about the silent ones. We talked about the quiet ones. The loud ones are the ones that I work on. In particular, what I do is I study the X-ray emitting region. So the X-rays is light, just like visible light, but it has a lot more energy than visible light. And this region of space that's emitting X-rays is coming from very, very close to the black hole. It's literally the material just before it kind of falls beyond the event horizon, never to be seen again. Right. So when I was talking to you about scales, and I kind of pointed out that, you know, the best picture we have is of a black hole on the scales of 300 astronomical units. By looking at the X-rays, we're looking at region of space that's 10 astronomical units. Okay, so the distance between us and Saturn, for example. So I can't take a picture of this. It's much too small to take a picture of this, but we can't study it indirectly in X-rays. Okay. Some of the stuff that we're doing at St. Mary's, what we're interested in is we're studying what the nature of this X-ray emitting region is. What is it? How big is it? What's the geometry? How does it kind of how does it connect with the accretion disk or with those jets of material that I showed you in Cygnus A and so forth? And studying that, we also get some physical insight about the black hole and the nature of the black hole itself. So this is some work that we're actually doing with a really keen group of students and postdocs at St. Mary's, and they keep me really busy. It's really a lot of fun working with them. But getting back to the X-ray, What are we looking at? Remember, I pointed out that when we look at the brightness, this was that IRAS 13224, we see this really kind of incredible flickering behavior, okay? So that is something that's pretty common, not to this amplitude necessarily, but that is something that's pretty common to X-ray observations of black holes. And this kind of indicates that the region of space is very compact, very small, right? Because it's moving so quickly, it must be very small. I want to talk about one particular observation. I won't spend a whole lot of time, but I just want to point out a galaxy that we recently looked at called NGC 6814. There's the optical image very nearby. I'm sure some of you actually probably looked at it. And this got a little bit of attention on social media when we published the paper last month. So it was kind of nice to see, and I'd like to share it with you guys. So when we looked at NGC 6814 in the X-rays, what we saw was a kind of a very unusual light curve. This light curve, basically the brightness changing as a function of time, it shows that part of it, this is, sorry, I should back up. This is about a day and a half long. Half the data, it showed very normal behavior, that flickering pattern that I kind of pointed out before. That's stuff that we knew about. But what was kind of unusual was that for about a day, halfway through the observation, for about the duration of a day, what happened was that we saw this persistent dimming of the source, and then it kind of flattened out for about another half a day. And then for about the same time as the dimming, it brightened back up to exactly where it was before. And this was kind of unusual, but I'm sure some of you guys might already kind of get an idea of where I'm going with this. This is the very same light curve pattern that you see in exoplanets. So some of you guys are probably really interested in exoplanets, probably have observed some yourself. I know Dave has done that before. And when you look at a planet moving in front of a star, you see this kind of behavior where the brightness is fairly constant when you're looking at just the star itself. As the planet starts to move in front of it, it starts to dim because the planet is taking a bite out of the star, all right? As the planet moves across it, you're in this low state. And then as it moves out of the star's line of sight, it brightens again. And this is exactly the way we interpret it. This is exactly what's happening in NGC 6814, where we have a cloud of material which is moving around the black hole. And what we caught was that this cloud of material moves in front of the black hole, the X-ray region close to the black hole, it dims. As it's moving across the face of the X-ray emitting region, we see this flattening, and then as it's coming out, we see it brighten again. And what this does is it allows us, we can calculate all sorts of things here. We can calculate the distance between that cloud of material and the black hole. We can calculate the properties of that cloud, and we can calculate the size of the black hole region, the X-ray emitting region. And when we did that for this object, and it was really kind of cool. The X-ray emitting region 6814 is about 3 astronomical units. This is the orbit of Mars. So basically, the black hole in NGC 6814 is probably about as big as the distance from the sun to Mercury, but then the X-ray emitting region is about out to the distance of Mars. So we're actually probing regions that are just so tiny, but these regions are located so far away in foreign galaxies. All right. So, yeah, so just to wrap things up, black hole research over the past I'd say maybe 20 years. I mean, there's been a lot of progress that's been made, a lot of groundbreaking discoveries, which have led to breakthroughs in science and technology. All right, we're taking pictures of black holes at the center of distant galaxies. All right, we're detecting gravitational waves now. All right, these are technological, massive breakthroughs. When we're studying black holes, why do we study? It sounds so unusual, but we're actually learning a lot about growth and evolution of not only the black holes, but galaxies. So we're learning more about how the universe actually formed and how things happen. And we're studying fundamental physics that we can't be studying in the Earth. I mean, the reason people ask me why I study black holes, and really truthfully, the most important reason to me is that it's really cool. I mean, it's fun. So thank you very much for your time. I'm happy to take questions.
Thanks so much, Luigi. That was very informative. And for a non-scientist, I understood everything you said, which is great. Thank you so much for everything you've presented to us. There were 3 questions that came through on the chat. The first one was from Dave Chapman, who said, must the mass inside the black hole necessarily be a singularity, or is it enough that it's all within the event horizon?
Yeah, so I mean, like, as far as we're concerned, it's all within the event horizon, right? It doesn't have to necessarily be at the, you know, how it's distributed within the event horizon, we don't necessarily know, right? So like I said, mathematically, it's a singularity, but it is really hard to imagine that there's a single point of space with that much mass contained within it, right? I mean, like that, I can't wrap my head around that. I don't believe that there's actually, that's what's going on physically. Mathematically, that's what the solution is. But yeah, as long as it's inside the event horizon, that's what matters for us.
Okay. From Galen Thurber, can a galaxy have no SMBH like a recently found galaxy? And can it be ejected?
Yeah. So, I mean, like, not all galaxies, there is a coevolution between galaxy and the black holes. Not every galaxy, we think that it's something to do with size. A lot of smaller galaxies won't necessarily have a supermassive black hole at the center, or it would be small. So there actually is this kind of, there is a relationship between the size of the black hole and the size of the galaxy, which is a really kind of unusual and kind of kind of pointing to one of my questions about, or one of my things about the evolution of black holes and host galaxies. Can they be injected? That would be a massive collision. I don't like saying no to something like that, but it's, I think that would be tremendous if the black holes could actually be ejected from the center of the galaxy. We definitely see galaxies that are merging together. And what often happens is that the 2 black holes manage to find themselves really quick, and they kind of merge together and grow together again. Whether they can actually get ejected, that's a lot of energy. So I'm not going to say no, but I'm not convinced it can happen very easily.
Okay, thanks. From Paul Heath, will the proximity of the sun affect the detection of the supermassive black hole collision?
I was thinking of that, the
Lisa?
satellite detectors.
With Lisa?
Yeah.
Yeah. So I'm thinking no. I'm thinking no. I'm thinking the sun. I'm thinking basically the frequencies are going to be too different or too small. So I mean, like, one thing everything is creating these gravitational waves, right? And one of the issues with LIGO, and the reason that it took over 10 years to actually make a detection, was that basically everything causes a disruption. Like a semi truck driving by 2 kilometers away is going to vibrate the ground and cause a distortion in those lasers, right? So all this becomes really, really challenging. But I don't think the sun is going to be a significant source of noise for Lisa. At least not the most important source of noise.
Thank you. Austin Dewar said, great presentation. If a black hole runs out of matter to consume, would the black hole shrink over time?
Over a very, very, very long time. And that's something that is referred to as Hawking radiation, and black holes basically cooling. But that would be, we don't worry about things like that in astrophysics, because the time scales that happens on is much longer than the age of the universe. So the time that it would take a black hole to kind of basically lose energy and lose mass would basically be much longer than the age of the universe.
Okay. That's it from the chat line, but I'll open it to the floor. If any members or guests have any questions, please unmute your mic and please ask Dr. Gallo.
Dr. Gallo.
Hi.
Hi, Blair Greenland, new member today. So I've read that black holes, they merge and they get larger, and that within the black holes themselves, that matter is destroyed and only gravity's footprint is sort of left. And that the ultimate fate of our universe is that the black holes will take in all the matter and eventually form one insanely big black hole, and then over time dissipate, and that would spell the end of our matter-based universe. Have you done any work on that?
I have not done work on that. No.
Okay.
That's actually kind of interesting. I mean, the ultimate fate of the universe. I mean, there's a number of different theories on what's going to happen, and I mean, right now it looks like we're kind of in this regime where we think it looks like it's expanding forever. But then there is ultimately this idea of a big crunch as opposed to a big bang where everything comes out together. It's really kind of interesting when you do the numbers and actually the size of the observable universe. When you calculate all the mass within the observable universe, the universe itself isn't much bigger than the Schwarzschild radius of the universe. So it's actually really kind of interesting when you type these numbers. What they ultimately mean is also, it's also difficult to interpret a lot of that.
And just one follow-up question. When you mentioned Schwarzschild, you're talking about the German who did the calculations during the First World War?
Yeah, Karl Schwarzschild.
Because Einstein didn't believe his own theory until Schwarzschild sort of put it together?
Yeah, Einstein, what was his quote? Mathematical curiosities, that's what black holes were, right? He called them mathematical curiosities. He didn't think there could be a physical counterpart to them.
Right.
Again,
And
this idea of having mass in a singularity is really kind of odd, right?
yeah, thank you, sir.
Yeah.
Tony Schilling, question. Hear me?
Sorry, I can't hear you so well.
Hi. When you say that we have a certain mass of the galaxy, I presume it's based upon observing the orbits of the various billions of stars. And but we also have black holes, and they're massive. They have a mass. So, what proportion of those 100 billion sun masses would be actually due to the non-supermassive black hole in the middle, black holes in general?
Yeah, so actually what's interesting is that the stars in the galaxy and even the black holes actually kind of still fit under the regime of being normal matter. Things like galaxies, like stars, I should say. The dominant mass in a galaxy is actually dark matter. So when you actually see it, the dark matter, the stuff that we actually don't see or don't have a good understanding of, is actually about 10 times more massive than galaxies in total. So they actually affect the orbit of stars more so than the actual visible stars in the black holes in the galaxy itself. So yeah, I mean, like I would point to say that they are orbiting the sun, and we do calculate the orbits, the orbits of stars, and we calculate the orbits of stars in order to determine the mass. But in doing that, we discovered that there's mass that is not in stars. So that's where our idea comes. There's more mass in the galaxy than there are that we can attribute to stars.
All right. So my real question was, how much of mass is due to black holes?
How much mass would be due to black holes themselves? So a supermassive black hole, there's likely only one in the galaxy. Okay, and this is based on observations of lots of galaxies. We only see one supermassive black hole at the center of the galaxy. Like I said, this is going to be a small fraction of the total galaxy of stars, so about 0.1% of the total mass of the galaxy. So it is rather insignificant. The number of black holes, remember black holes, the way we know how to form black holes is from those very massive stars. And those are actually quite rare. Now, when you're looking at a universe of stars, there's a lot of them. But when you're talking about, relative populations, then there aren't so many, right? So we're talking about stars that are more than 40 times more massive than the sun. Those things are the ones that are creating black holes. So it's not just like, they aren't as common as we probably think. it's only when you look at the entire universe that you see so many of them, right? So I would say at most you're looking at something that's on the order of 0.1%.
Thank you. And
Question,
for the
Luigi?
last question, from Shane Fetchner, and I apologize if I didn't pronounce your last name correctly, but from his 11-year-old son, when did you first discover your interest in black holes?
A long time ago. I was probably 11-year-old. Yeah, I mean, I was always kind of one of these kids who liked looking up the sky, and I've got stories about that. You know, going to my relative's house and just they lived out in the country, and I'd be coming back home and we'd be looking out the window at the sky at night. And I mean, that's just kind of how it all started. Black holes, I mean, like, I don't know who's not interested in black holes. I mean, really, I mean, like, yeah. So I mean, like, I think I started studying black holes in grad school, but I was always kind of interested in it. That picture that I showed you of Cygnus A with the jets going out, and I said that they're 300,000 light years. I mean, that was one of the first pictures I saw when I was in university, and that kind of like, I was like, yeah, that's cool. So that's kind of what probably got me into black holes.
Great. Well, thank you again so much, Luigi, for coming today. It's been really fascinating. And as you suggested, we will be in touch in a couple of years.
Okay, awesome. I look forward to it. Hopefully we're in person.
Yes, hopefully by then. Yes. As well, for those of you that were late in joining us, please note that this is being recorded and it will be up on our YouTube channel within 24 to 48 hours. So if you missed any portion, or for those of you that attended the whole thing but would like to see it again, it'll be posted for you to see there. So again, thank you, Luigi. Our next guest is a member of RASC, Michael Gatto. He's been a member since 1998, and new to me, information to me, is that he was a former editor of Nova Notes. He has done a lot of sketching. He's done the Messier catalog, the finest NGCs. He's done about 100 of the 400 Herschel 400s. And he's done countless planetary sketches. And if you remember the, one of the last ones of the journal, his sketches were featured on the back cover of Mars. And that was one of the reasons why I invited Michael to join us today, is to inform us as to how he sketched and digitized those pictures. So welcome, Michael, and I'll let you take it over. Oh, you're muted.
That's embarrassing. I've done this so many times at work. I thought I would have had it down, but oh well. Thanks for the invitation to speak today. Before I say anything, it's really nice to see a lot of familiar faces. I haven't been at a meeting for ages and ages and ages, but I recognize so many people here, and it's really great to see everyone. Yeah, so I've been around since 1998. A big visual observer, not so much into photography. I've been sketching pretty much every observing session I do sort of produces some sort of sketch or another. So I have lots that I could talk about, but the focus today is mainly on the recent Mars sketches that I produced during the last conjunction. Yeah, so I do have that journal back cover framed on my office wall. And I do want to say hi to James, because I feel in some way this is me presenting to my boss in some ways, because we've worked together on the journal for so many years now. It's nice to see him in semi-person. Okay, so I didn't exactly know how to do this the best way, but what I thought I would do, I thought I would do kind of like two parts. So a little bit of a sketching demo, which I hope people find interesting. The demo is specifically Mars related, but it would apply to any kind of astronomical sketching, especially the moon. The techniques I would do here would be the same as I would do for any kind of moon sketch. So what we're really talking about are these visual observations. So hopefully you can see my screen. On the left here is a pencil sketch, which would have been done at the eyepiece of my telescope. And then on the right is a final kind of digitized, colorized version that I was using to either get published in the journal or share online or just have for my own kind of sake. The equipment I use for my sketching is primarily an 8-inch f7.5 Newtonian, which is just on a dot mount. So I'm finding everything just with a Talrad or a finder and then hand tracking as I go. So generally I would observe for anywhere from half an hour to an hour. And then a sketch might take 5 minutes, 10 minutes. It's really hard to say. It just depends on the situation. So I'm going to show you this. So the best way I thought I would do it is to maybe just do a little film of me kind of sketching an object. So I took one of my Mars, one of the Mars drawings I had already completed, and I just drew from that for now for the purpose of this kind of demo. So I'm just going to back up. I did another one, autoplay. So I don't have any like real fancy equipment. I would have like more or less 3 pencils. You want to have like a nice hard pencil, like a 4H or 6H for doing light line work, like a medium tone pencil, and something dark like a B or 3B, 4B, just to fill in those kind of dark areas. You'd want to have like a paper blending nub, I think it's called. And then I also have this kind of like almost like a pencil eraser that you can sharpen and get like a really nice kind of fine tip onto, because you kind of draw with both the pencil and the eraser as you kind of go forward. So I don't have any fancy paper. I usually just use computer bond paper that I just print out my observing sheets on, and I kind of go from there. So I would start to draw an image circle. I'm going to maybe I can't speed this up. Yeah, so I think for most of my Mars sketches this time around, I was using like an image circle that was 34 millimeters in diameter. So I would just trace that out in ink to give me like a place to start. Just hold on 1 second. Yeah, I think if I do it this way, I can speed it up a little bit more. Yeah, so here I would start with my image circle. And then the first thing I would do is take a medium grade pencil and fill in the whole area with a bit of tone. Because there's nothing on the drawing that's going to be like pure white, which would be the white of the paper. And there's probably not going to be anything in the drawing that's going to be like a pure black. There's always going to be kind of shades in between. So if you kind of start with a medium kind of grade tone over the whole drawing, it gives you a nice way to sort of add darks and then remove lights with the eraser. So again, I would just take like a hard pencil, like a 4H, and just start to block in any kind of major, like sort of dark and light areas that I might see. I would always start with the southern polar cap, if it's visible, just kind of get that in the right place, get the size right, and then just start kind of blocking in like features. And it's really like a sort of additive reductive process. You kind of add things in and take them away, add them in, take them away. And the whole time you're kind of sketching, I think the key is to kind of look at, you know, the scale of the thing you're sketching in relation to the kind of object size itself. So if I take this dark area down here, I want to keep referencing the view in the telescope to make sure that if I've drawn that down so it's halfway through that image circle, then I want to make sure that I'm halfway too. I don't want it to be too small, too big. And I find the easiest thing to do is to kind of exaggerate features and make them bigger than they appear in the overall scale. So as I kind of like block darker areas in, you can take the blending stump and then start to kind of like just soften all that line work out, soften out those kind of tones. I've kind of drawn in the north polar hood, which was quite visible for me most times I observed. And then I would go in with sort of the eraser and then start to really shape out those kind of dark areas. I want to take out all the kind of pencil lines. I want to lighten down the overall tone to get those kind of brighter areas of the planet to kind of show up the way I want them to. And then again, if you think, you know, if you kind of keep looking back to the image in the scope, you have to kind of just keep gauging the contrast. Is this way darker than what I'm really seeing? Do I want this thing to be bigger than it really is? And just kind of keep kind of checking yourself. There was like a kind of bright area just under the south polar cap, which I kind of put in, and then I think I decided, well, maybe that's a little bit too dark, so I might want to blend that back out again. So like I said, you kind of put things in, take things away, put them in, take them away. But it's tough too, because it's not a stationary object. So most of your time you're going to be kind of like observing and not really sketching. You're just trying to capture those fleeting moments of kind of really good seeing when they happen. So that's my little demo sketch of how I would work right at the eyepiece. And then I can show you the actual observing form that came out of that. So here's two different nights of pretty much the exact same same rotation. So this is the sketch I drew from. You can see this is the one that I produced right at the eyepiece. That's very similar. The technique would have been exactly the same. And then this is almost the exact same view. This one on the left was from September 22nd at 12 a.m. start. And then on the right, September 26th at 3:40 a.m. to 4:40 a.m. But you can see the difference in just local conditions and how much of a drastic change. Really, it's the determining factor, I think, in any kind of good observation is how good the seeing is going to be. Because these are like the exact same features. It's Solis Lacus, the eye of Mars, it's called. But in this night, it was very obvious it was a nice shape. But on the night of excellent seeing, this kind of dark bar that comes underneath was much more prominent than it would have been in the image on the left. And the whole area itself had like a way different contrast feel than the kind of brighter areas below it. And the actual shape of the kind of protrusion itself was different. It felt on this night like it was a little bit of a claw. It almost had two little kind of endpoints that were apparent to me that I wasn't seeing, just a few nights earlier. So again, it's kind of your interpretation of the view that's presented to you at that time. And yeah, and like I said, local conditions are really, for me, like the #1 determining factor. Yeah, so I knew 2020 was going to be a really good apparition or conjunction. I look back through my sketches. I have quite a few binders now of astronomy sketches that I produced. And I have a section on Mars. So I did have about 10 sort of this quality sketching observations from 2003. And then in 2005, I think I had about 12 that were about this level. 2003, I didn't get a full rotation. There was some features or views that I missed. 2005, I did get a full rotation, so I was super thrilled about that. I think from one of these sessions, Dave Chapman actually took one of the sketches and used it on the Observer's Handbook cover, which was a pretty big thrill. It was very exciting. But then from 2005 to 2020, I only have maybe 1 or 2 random sketches. I didn't really get back into it too much. So I knew this was going to be a good year based on all the chatter on the RASC channels and the internet and the local mailing lists, obviously. And I was seeing some really good results from the National Astro Sketchers list of the RASC. Like, I know Chris Beckett was getting some really good observations really early on. So I was like, well, it's really encouraging. I'm really going to try, whether it means getting up a lot or trying as much as I can to get that kind of full rotation. And then once conditions were good and the weather was good, and I saw like other observers like Dave Chapman was on the RASC, email list. He was also contributing. So I was like, oh, this is exciting. I want to be part of this and really kind of capture it. So in the end, I did get pretty much full rotation. Like Judy showed, this was the back cover of the journal. This was not every sketch I did, but more or less the bulk of the main features. And you can see like Certus Major's in here twice. And so it was Lacus is in here twice. So I felt like I did at least one full good rotation, maybe even two. So I was super thrilled that we had that much amazing weather for me to be able to do that. It was really quite surprising. So the next part will be how do I kind of digitize them? And I think I'm just going to do like a real-time kind of Photoshop kind of walkthrough. So to get from a sketch that I have on a paper, like my observing sheet like this, I would either scan the sheet or I would take a picture of it with my phone. Because I find the scanner that I have is a printer scanner and it seems to blow out the whites a little bit more. I find with like a cell phone or an iPad, I can control the dynamic range a little bit better to make sure that the scan isn't kind of losing some of the data. So this is a re-scan I did this morning of the sketch that's in my observation book. So the first thing I would do obviously is that, you know, I don't need all this extra stuff here. So I brought it into Photoshop. I'm going to crop this down to a more usable area. And then let's move him up a little bit more. So that's probably too much. So the first thing I would do is kind of, this is probably going to be hard to see. It's really hard to tell what's going to be transferred across to the screen share, but hopefully it kind of makes sense. I'm going to duplicate this base layer scan because I never want to destroy the actual scan itself. You always want to work non-destructively. So now I have this base scan that I'm not going to touch again, and I have a duplicate. So on the duplicate now, the contrast is wrong. So at this point, I would sort of adjust the photo quality itself. So I would come in to, I could use brightness contrast, I could use levels, I could use curves, exposure, the camera raw filter. Like anything in Photoshop, there's 25 ways to do the exact same thing. So it's whatever you sort of feel comfortable with. So if I do just a quick kind of levels adjustment, I might want to open up the whites a little bit more. I don't want to blow everything out so I lose a lot of the sketch quality. And I don't think I really need to make anything too much darker. So I've adjusted the levels here so you can see from the scan to the adjustment, the changes that's made there. I don't want to have the final sketch obviously have that black ink outline. I don't want all this mess on the outside of it. So what I'm going to do is make a mask for all the layers that come after this one. So I would take this circular object tool and I would make myself a shape. So I want to be right over the drawing. So I make myself a shape, which is probably a little bit smaller than the drawing itself. So I just fill that with white. So here I have the shape layer in my Photoshop file. I can reposition that and get him where I want it to be. And then I'm going to use that shape layer as a mask. So I'm going to take the adjusted scan and move that on top of that layer so it's above it. I'm going to hold down my Option key and nest that into the shape itself so it becomes a mask. And I'm also going to do one more thing. I'm going to add a white layer just behind this one so that I don't want to see the base scan underneath and I don't really want it to be on a transparency either. I'm going to select all of that and fill that with white. So now I have my sketch, which has been minimally adjusted. I can push it around inside the circle a little bit more. And then I have this nice kind of hard edge on here as well. So the next part would be to add the color. So what I'm always trying to do is not destroy the integrity of the sketch or blow it or obscure it as much as possible. So in this case, I would take the rectangle tool and I would make another shape here. And here's where I would pick the color for the background of the kind of brightest overall parts of the planet itself. And there's no rules here about this in any way. People were asking me as I was sketching, you know, what color do you use for that fill? Like it doesn't really matter because it's really how I interpret it in that moment when I'm at the eyepiece. And truth be told, if you were trying to do this in an accurate way, the images in the scope are so low contrast that it would be almost impossible. It's almost like very fine shades of tan over a slightly lighter shade of tan. So it's really, this is where you can sort of take a little bit of artistic license. So I would maybe pick, again, it's just is really like a preference and how you feel sort of at that moment. But for something like a set where I was making them for the RASC, I had to make sure, or for the journal, I had to make sure that they're all the same. So they felt like they were done at the exact same time by the exact same person. So I'll just pick this guy and pretend I'm happy with that. So I now have this rectangle shape with a fill on it on top of my scan. So normally what I do is I set the opacity of this layer, usually to like multiply. And then you can go through, there's, 25 different methods of adding this layer to the layer beneath it. You kind of play with sort of what you feel like makes the most sense. So let's say this linear burn one, if I like that one. And if I don't like the color I picked, I can always double click on the layer itself and change it to see maybe that feels better. I can adjust it, kind of go from there. And then I want to put the shape layer itself into this ellipse mask over top of the scan. So I'm going to hold my option key down and click that. So now this layer also lives inside this mask with the scan itself and the color. And again, I can change the opacity on this. I can just fool around with the color without really doing anything to the underlying scan. So now I want to put in some of the kind of lighter features. So the North Polar hood and the South Polar cap would be sort of the brightest parts of the scan. So I might sample this kind of brown area from just the color added to the scan and maybe blow that out. Probably not like fully white, but sort of like a tone in there. So I now have another layer here, which I'll call polar cap. I would take a paintbrush and I would just go in here. I probably wouldn't do like 100% at a time, but I would try to build this up a little bit more. So you can see I'm kind of getting that area like a little bit whiter now. I can come in a few times and just kind of get it to where I think it kind of looks right. And then if I want to use more of actual white, I can change that. And I just keep kind of painting that up until I feel like it's kind of accurate to the view that I remember or saw at the eyepiece. And then any other kind of light areas you want to fill in, I would then add another layer. We'll just call this maybe haze. And then I would just fill in the exact same way, just take this brush. So there was like this kind of lighter area here, but that's way overdone. So I can drop the brush down to maybe like 20% and just kind of add in a little bit of detail here. The North Polar hood was like a detail. So we'd want to kind of brighten that up a little bit. Usually along the edges, there was some haze. I was noticing. So I'd probably want to put a little bit of that in. And then again, take this haze layer and put that inside the mask as well. Oops. So now everything is confined by that kind of outer circle shape. And then I can show you what this looks like on dark. So if I make like a black layer, so now I can take that black layer and bring that down to the bottom, just above the white one. So you can kind of see it sort of coming together here a little bit better. And then sort of as a final thing I would do is put in one more layer and just call it dark features. And here I would just put in any areas that I thought needed like a little bit of a contrast boost, because there's usually, if you kind of look for a while, you can start to see some areas that are just a little bit darker than other ones. So I would probably sample like one of these brown areas from the scan itself. And I would just start to add in just a little bit of tone just to bring out some of these kind of features. And then again, that dark feature layer would live inside of this one. And if I take my base scan that's on the bottom, just for an example, I can bring that up to the top. And we can just kind of flip between the two of them. So again, even though it's colored and digitized, I try really hard to not take away any of the initial scan quality itself, or any marks that I put in the drawing at the observing session. I don't really want to take that away, because you can sort of get caught up in adding features that you may not have really observed, taking things away that were there. So I just try to be as realistic to the moment I was kind of doing the drawings in at that time. And then once you get it in this format, this edge on the outside here might be a little bit hard. So I can take the mask itself. I can add a bit of blur to that. I can rasterize it, and I can sort of like just clean that edge up a bit, because you're never going to get that kind of sharp of an edge as you're observing. And that would be pretty much the whole process of how I would get all these sketches sort of digitized into this kind of format. And like I said, for lunar observing it, the process would be the exact same. You would take your black and white moon scan, change the levels on that, put like a gray overlay over the whole thing to color the whole lunar surface, and then add in layers of white, and then start to paint in sort of where light is hitting sort of raised surfaces, and sort of get that shadowing all kind of worked out. So yeah, so that's hopefully a bit of a glimpse of how you kind of go from a sketch on the right to an image on the left, or vice versa. I just messed that up. So yeah, so that's kind of all I had prepared for today. You kind of said keep it about 20 minutes or so. So I tried to keep it about there, but yeah.
Well, that was excellent, Michael. You make it look so simple. I'm sure those people that are familiar with Photoshop will certainly find that intriguing, and how they can change their sketches into something that has some color to it. There was a question came through in the chat. What kind of light do you use while sketching from the telescope?
If it's for planetary stuff, it's easier because you don't need the dark adaptation that you would need for doing deep sky stuff. So for these, it was nice. I didn't need like a dark sky. I could just go outside and keep like a dim, almost like a white light. I think I mostly use like an amber light to keep it a little bit. You don't want to blow your eyes out too much, but because the object's pretty bright, it's decent enough. It's much harder with deep sky stuff like from St. Croix. With a red light, obviously you got to keep your night vision in check as much as you can.
Okay, that's great. I'll open that. Came from Hugo Lama. I'll open the floor now to other questions if members have questions or comments. Okay, well, thanks again, Michael. Again, congratulations on the back cover of the journal. Your sketches, when your emails come through the various discussion lists, still blow us away every time you post them. They're absolutely incredible. So thank you so much for your ongoing work in that. And thank you for today's presentation as well. I'm sure some people will have benefited from that.
Yeah, I hope so. And thanks for the invite. It was a lot of fun.
So if you get a back cover again on another topic, we might invite you back.
Excellent. Well, we always, Grant is my work partner that we do the journal with, and he picks on me sometimes. He goes, "Oh, you got the back cover, so maybe one day you'll get the front cover." And I said, "I doubt that's going to happen, but who knows?"
You hear that, James?
I'm not the editor. I'm only the production manager.
Yeah.
However, it is a collaboration that we do. It's a lot of fun working with Nicole, and Michael, and Grant. We have good times together.
Hey, Mike, I gave you the front cover of the Observer's Handbook.
Yes, I know. That was a big moment. And someone, I think it was Randall, brought it up this year, that I was on the cover that year too.
So here's the story. I asked Michael to send me his drawings of Mars, and he did. And I decided to use one of them for the cover. And so I put it in the cover. And of course, Michael was my graphics consultant. So I casually sent it to him. I said, here's the cover for the handbook. Let me know what you think. And I guess he opened it up, and he opened up and saw his his Mars drawing. And he said he was surprised, but I don't know what he thought I was going to do with those drawings.
In my mind, it was going to be like a montage, like a grid. Here's a picture, here's a sketch, you're one of 10. Yeah. And I got it, it was like, bam, just the one image. I was like, whoa.
So it was the 2012 edition, I think. And it was a bit of a joke because
James has
it. Was,
oh yeah, there it is.
Yeah, so that year, it was 2012, correct?
Yes.
Is that right?
Yep.
So that year there was a transit of Venus, and I had a picture of Venus, and that went on the back cover. But I really like Mike's Mars picture. So I had Mars on the front cover and Venus on the back cover, you know, that whole thing about men are from Mars, women are from Venus kind of thing. Anyway, that joke kind of went over everyone's head. But the after story of that is people kept on going on about this amazing photograph of Mars that was on the front cover of the handbook. And I said, look again, it's a drawing. So
yeah, and process-wise, I don't do this any different than I did that one or anything earlier. I do work more on an iPad now, but it's basically the exact same process.
Well, I have to say that you're, especially Mars drawings, but other things are a great inspiration to me. And whenever you compliment what I've done, I feel like maybe I'll get there one day. So. It was fun this fall, though, wasn't it? It was fun watching Mars.
Yeah, it was. And I like the interaction. Like, I'd be like sketching, I'm like, I hope Dave Chapman's seeing this. And then I'd kind of go to the list and you'd be like, there's a sketch. I'm like, well, there's my sketch. And then I'd like compare the two, and then other people throwing photos in. Like, yeah, it's really great that you can go track down pictures and other drawings so easily and just compare them.
Yeah, well, it's a lot different now than it was 15 years ago, for sure.
Oh, absolutely. Yeah.
And the other thing is that, you know, I'd go out and I'd go, man, I'm just so tired, I can't observe, and I go to sleep, and then wake up the next morning and Mike could be going, the seeing was like excellent last night, you should have been up. And I was like, So.
Okay, well, thank you so much. And we look forward to seeing you online with future sketches.
Thank you.
Lunar.
Judy.
Sorry?
Judy, it's Paul.
Yes.
Sorry. I want to add one more thing to Mike's presentation here.
Sure.
Michael, you mentioned briefly what telescope you're using. Can you tell us where the optics are from? You did mention it's an 8-inch, but it's an f7.5. And I think that's one thing a lot of us don't realize when we're looking at planets is you're using a very long focal length mirror that's very easy to figure, and it's probably really well made. So can you elaborate on the optics?
Yeah, sure. I bought the mirror set from Gary years and years ago. I started with like a 6-inch f8, which was just a commercial Celestron scope, but it was really good. And I was like, well, now I know what I want in, for like optical quality. So Gary Weber had this 8-inch f7.5 mirror that he bought just on a whim and didn't really have a telescope built around it. And I knew I would rather sacrifice aperture for like optical quality. So like you said, it's long for an 8-inch, like an f7.5. It's actually right there. You can see it just in my office here, that big tube. So when I'm standing, the eyepiece is exactly at my eye. So it's quite long for like an 8-inch scope. I wish I could sit down and use it more. That's one thing I would say. But optically, it's excellent. It has a very small, like a 1-inch secondary. So the focal plane is very close to the tube edge. So I don't think I could use that scope with 2-inch eyepieces. But it gives me a really small central obstruction. And the mirror was made by Carl Zambuto, who, I don't know if people follow probably mirror makers like they would have maybe 15, 20 years ago, like I used to. But as soon as Gary said it's a Zambuto Optics 8-inch mirror, I was like, I have to buy it. And I spent a fortune on just the mirror and the secondary, and then built the telescope up around that. But I've never really had any kind of like aperture fever because I know I couldn't get the optical quality that I want in anything much bigger without spending just more money than I have. So that's sort of why I've been happy with like an 8-inch scope for sort of all these years.
Can't go wrong with the Zambuto mirror.
No, and I'd have to dig out all the paperwork, but all the like the testing and the straw ratios and all that stuff is just, the numbers are off the chart. But I've always found that the only limiting feature of the mirror is its physical size, and as good as the seeing is going to be, it never like tops out. It's the atmospheric conditions that always limit kind of what you can see.
Okay. Thank you so much. Thanks for the question, Paul. Speaking of Paul's, next up we have Paul Heath. Paul is our, and I'm going to get it right this month, he is our outreach chair. Has been for a few years now. He's also a member of our board, and Paul is quite active in outreach, and he's also an author of his own book of poems, and he'll present a new one to us today, but I'll let you discuss. I think you wanted to talk about the Starfinder today, Paul.
Yeah, I'm sort of running out of ideas for the youth presentation, but most of us are quite familiar with our Starfinder, and but there's different aspects of it that aren't always aware, like people aren't always aware of. We do have an online presentation by Andrea Meisner with the Haley Davis filmed a few years back, and it's on our YouTube channel. And also RASC has a paper version, a black and white paper version you can download and print out for it as well. One thing I like to try to emphasize on the Starfinder, of course you set the date and time you want to observe, but one of the things I'm always asked is when's the best time to see something, and I usually focus on Andromeda, the Andromeda Galaxy. So if you set it for midnight in the first week of October, you'll find that the Andromeda Galaxy is down in the southern hemisphere, is high in the southern hemisphere. And that's usually the best time to see any of the objects. So what I tell people is when you're looking at what's down here in the southern sky, high up in the southern sky, that's the best time to observe it. It's the highest in the sky and it's easiest to see. Also, the month will indicate the best time of year to see it. So for Andromeda, between mid-September and mid-October is when Andromeda is highest in the south. So if you're looking for any particular object, you want to set your star finder for when, put the object in the in the southern hemisphere as high up as possible. And then the 2 months at the top will give you the range where you can visually see the object at its best. And for photography or for sketching or for doing your Messiers or any other type of observing program. And that's one thing that is sort of counterintuitive. But if you find the object high and low in the horizon, it's very hard to see, very difficult to get photographs of that. So there's one thing with the star finder that most people aren't aware, is that you can use it to actually find the best time of both the night and the year that you can observe the object. And of course, it also find out what's up on your birthday. So, but I recommend that you go to the Halifax Center's YouTube site, because Andrea's talk gives a good outline on how to use the star finder. It's a great beginner's tool, and even as a long-time observer, I use the star finder quite often, especially if I'm with a youth group. Well, we'll talk about that and we'll set it up to look at particular objects. So we try to look at things that are high in the south. So with this in mind, you can set up your observing program, or you can set up your program to show objects out for outreach ahead of time, and know what's the best objects to look at in that particular night. Because it's always good if they're not disappointed. If it's high in the sky, it's easier for them to find. And if they find it, they're less disappointed. If something's on the horizon, they're fighting between trees, etc. So it's one aspect of the star finder that most people may not be consciously aware of, but it's a good tool, especially for outreach, for deciding what it is you want to show people on any particular night. And I recommend go to the YouTube channel and watch Andrea's presentation. It's excellent. Okay, that's about all I had. I'm still working on my other things, so hopefully in the future I'll have some longer presentations.
Would you like your poem now?
Yeah, I can do that. Food for the Soul it started when I was president of the club, trying to make the sort of my thing in the meetings. And I've always written poetry, and I decided I'd write poems based on the topic of the evening. I didn't do one on black holes, unfortunately, this time. What has been in the news lately is that last set of satellites that have been launched, a cluster of satellites that are now starting to inundate the night sky. And my idea of this poem is what's going to happen if this goes to its extreme, it goes to its final conclusion. So basically, this is the poem that says, here guys, this is what could happen. So, last star. They moved into the darkness, skies filled with sparkling wonders, the long glass moving, wonder to wonder. Enraptured, he followed his father's lead. She followed her father out into the darkness, majestic the skies, sparkling and shining so bright. With indrawn breath, a new wonder they watched. Steady, the gleaming light drifted across the stars. She took her son beneath the darkening skies to show him wonders stretched across the skies, to tell the tale of the first, as gleaming light sped now between the stars. He took his daughter far from town. The ancient glass still wonders found. A sudden gleaming glow rose high to cross the sky. The stars, a magic floating home now held. She took her daughter far from town. A hill she knew where wonders once did abound, but the distant glow did mute the stars as lights from all directions outran the night. She took her son far from their town, dazed the drive in search of darkness. The ancient glass pulled wonders from the night. quick between the rushing lines of circling lights. He took his daughter into darkness. So far from home they wandered, brief the glance within the ancient glass, faint the stars between dashing, glowing lines of light. She had the stories from all the years, the journeys the ancient glass had made, filling up with wonders of the skies. Hers alone now, together with a desperate task. She traced each step the ancient glass had made, yet unfound the wonders of the tales remained. Then a thought lit up her night. Each glowing bead a circuit mapped in detail made. Their paths from out the clouds she claimed, a glowing picture built of shame. And then her eyes beheld a spot. Quick she pulled it deep within her heart. In hope and wonder to its starting point, cradled loving, the ancient glass was brought, set with gentle care, and then to her eye she dared a single gleaming mote, unmoving upon the ancient glass rested there. Then the last star from earth with her sun did share. Just sort of what might happen, folks. We're putting so much stuff up there in the sky now, it's harder and harder to see things. And Blair, your photographs may get smaller and smaller all the time. Or just pictures of streaks. Hope you liked it.
Thanks, Paul. Certainly food for thought.
Paul, one comment, it is getting more and more difficult to get a picture around Orion these days. There seems to be an awful lot of Starlink going by there.
Yeah, and they've got launches planned for that group in Europe, and then Amazon's talking about throwing some up into space, and everybody's going to throw their own up there, and eventually we might only have one star left to look at. So.
Well,
the only good thing is you always know where they're at. You can go online and find out exactly where they're at. So that's about the only good thing about it.
well, it may come to the point where we'll have to use all these telescopes that are up and above them to be able to access those in order to get the pictures that we're looking for. But hopefully it doesn't come to that. Okay, well, thank you. Next up on our agenda is our observing chair, Dave Chapman. Who'll do What's Up in March, Dave?
Okay, so this is the What's Up for this month. As again, made with the Observer's Handbook and Sky Safari. Now the month's already underway, so a few things have already happened, but I've tried to tell people about them. So as usual, I start out with the sun this month. For those that are watching, I'm not going to follow the links, the hyperlinks in this presentation. It gets too complicated with Zoom. But if you go to the Halifax Center main page website, you will find a PDF of this presentation there. And if you open the PDF and go through it after, those links, those URL links are active. So up in the right-hand corner, if you want to see what's going on the sun, you follow that link. So solar cycle 24 is definitely over. And we're starting solar cycle 25, although it's taking a long time to get started. So these things aren't very predictable. You can have long minima between maxima, and so people are keeping an eye on it. I don't think there's much going on right at the moment. A couple of months ago, we had a big sunspot, but that's where you go to find out what's going on day by day. So there's two things that happen sun-wise, time-wise this month. And I'm wondering if anybody can guess what they are. Anybody out there? There's a clue in the graphics. Two clues, actually.
We jump ahead, don't we? Or,
Yes, you're right. There's what happens is solar noon. It's already a little bit past clock noon, and that's the vertical line at the bottom, almost vertical line. And then as of the 13th, I guess, or the 14th, we go to daylight saving time. So that shifts everything. The clock shifts clockwise by an hour. So that's shown in the graphic there. What's the other thing?
Daylight is longer than night.
Yeah, you're right. If you include dusk and dawn with night, the daylight gets longer than 12 hours. It goes from 11 and a bit hours to over 12 hours, almost 13. And that's because on the 21st, or the 20th, we have the equinox. So there, give yourself gold stars for seeing that. So dawn's getting earlier, and darkness is going to be later. Notice that by the end of March, it won't get fully dark until 9:22. That's a big change from now. Most of that is because of the daylight saving time, or daylight stupid time, as I call it. The other part of it is that at the equinox, the day is changing very quickly. Like the length of the day is changing most quickly at the equinoxes, and there's a lot more minutes every day at the time of the equinox than at any other time, and so you really start to see it take off around now. And so hopefully by the end of this month, I've got some seeds out in my winter garden, and I'm hoping that I'm going to see things sprouting under cover because of the long, the heat for one thing, but mostly because of the long daylight. So the altitude of the sun is increasing quite a bit. So the time to observe is shrinking, but it's still fairly civilized. You know, you can get out there and do some nighttime observing before midnight. So hopefully you'll get out and it might not be too cold, so you might be able to get out and do some observing. As far as the moon is concerned, we just had the last quarter yesterday. If you are an early riser, like Dave Hopkin apparently is, Dave Hoskin, the waning crescent moon parades by Saturn, Jupiter, and Mercury in the southeast before sunrise, but it's quite difficult because the ecliptic is quite low, or quite shallow in angle, and the moon is well below the ecliptic. So by the time the moon rises, it's actually quite bright in the morning. So it's a bit tricky to see the planets and the moon before sunrise. I tried the other day, and I saw Mercury and Jupiter in my binoculars. I saw Jupiter by eye. I could never find Saturn. I had to get even earlier than I did in order to see. I will have to do that earlier. Of course, if you were in the southern hemisphere, it would be great elongation for Mercury and the other planets. The new moon's coming up on the 13th of March, pretty soon, next week. And that, for the Mi'kmaq, the maple sugar moon, Sukewi goose, which another way of saying spring moon. And again, if you follow that link on the PDF, it will take you to the video of Curtis Michael teaching you how to say that, Sukewi goose. On the 19th, the moon and Mars will be within a 5-degree binocular view. It's always fun to look at those things together in the sky. First quarter is on March 21st. And I think, I'm going to say more about this in a minute, and then the full moon's on March 28th. So as far as observing the moon is concerned, these are the, here's a chart of the things that are listed in the Explore the Universe guide, which pertain to the moon. There's 12 craters and 12 mare, and here's how you find them. And by the way, Mike Gatto created this diagram based on one originally made by Roy Bishop. Both of those men are in attendance, and I thank them for their contributions. So the best time, well, you can see the moon anytime, but it's really in the springtime. It's really on view around the first quarter. It's high up in the sky. So March 20, 21, 22 is just after sunset. You don't have to wait for it to get dark. It looks beautiful in the twilight. So this is a good time to observe the moon and catch some of those events. The red circle on the plot there, it circles a couple of minor craters called Werner and Alcyensis. And the reason I circled that is because just above those, if you go from the slightly bigger one to the slightly smaller one up to the left, where you think there might be a third crater, that's where the lunar X appears once in a while. And that's what I'm going to talk about next. On the 20th of March, which is the equinox, and technically the day before first quarter, you will be able to see the lunar X. Now, I've simulated this in my software, and my advice to you is that you need to get out there right about sunset, because it's going to be well underway here in Halifax. So if you want to catch it, look earlier rather than later is the time to look. So the backstory on this is, again, I didn't claim to have discovered the lunar X. I'm sure that lots of people saw it before I did, but I discovered it for myself at Nova East on 2004, August 24th. And here's a picture of me with the telescope that I used. I don't know, that about the same day, I guess. The story is that we were there. It was, if people remember, it rained Friday and Saturday. We had no observing. Sunday morning, we got up and everybody was packing up to go home when it was a beautiful sunny day, and it promised to be very clear at night. So many of us decided not to leave on the Sunday morning and to stay one more night. And we all trooped down to the office to pay our camping fees for one more night. And I think about a third of us stayed. Chris Beckett was there and a few other people. And as I was getting my telescope set up for an evening of observing, I decided to, in the twilight, I decided to train it on the moon and get it all focused and set up. And I saw this X on the moon, which is just a bit of the lunar topography, which catches the sunlight at the right time. And it really stood out, and I got quite excited and never seen anything like it. And a bunch of other people had a look at it. Tony Jones took a picture. Chris Beckett was trying to sleep and was yelling at me to pipe down. He remembers it well. He was camped right next to me. And if you want the whole story on this, it's written up in RASC, not just that event, but all the things that subsequently occurred, which was me getting interested in it and trying to figure out why nobody seemed to know about it, figuring out how to predict it, all the different methods, observing it many other times using those prediction methods, and gathering up a group of people to observe it during one apparition all across Canada, so we could get observations of it in all phases of its waxing and waning. And all of that's in that article. So the subtitle of that article is Everything You Wanted to Know About the Lunar X, but Were Afraid to Ask. So if you have any questions about that, read the article. And if you still have questions, I'd be happy to answer them. So remember, mark this on your calendar. If you have an observer's calendar, it's already there. But I would just add, do it early in the evening, don't wait. So the planets in March, I said, very low in the dawn sky. I found it the other day. It's already had a close conjunction with Jupiter. I caught it the day before. I guess it was today, greatest elongation west. So tomorrow, I don't know if it's going to be clear. I forgot to look, but you can still catch it. It's pretty low above the horizon. So you have to catch it you know, I say 20 minutes before sunrise, but it's actually probably worth looking earlier than that because the sky will be darker, although it'll be lower. So there's a bit of a trade-off, and you'll probably need binoculars, but you definitely need a clear sky at the horizon. If you have clouds, don't just forget it. And you have to go somewhere where there's a good horizon. If there's any trees or houses around where you are, you won't be able to see it. Venus is out of the picture. It's headed for a superior conjunction in end of this month. I guess with difficulty you could find it before sunrise if you like that kind of sport. But the good news is when May comes around, you'll be able to see it in the evening sky again, which will be nice. It'll move from the morning to the evening sky. Mars is still up there hanging in. It's not as bright or as big as it used to be during its conjunction or its opposition time. It's already past the Pleiades, although it's still probably pretty close. And I already mentioned it's near the waxing crescent moon on the 19th, but I don't know if it's going to be clear tonight, but it might be worth a look with binoculars. Jupiter and Saturn are in the dawn sky, but not really easy to observe. The other solar system thing that I should point out is that right now, and then again at the end of March, is a good time to look at the zodiacal light in the western evening sky. So you need a dark sky regardless. You can't do this in the city. You need to go somewhere where it's dark, in the west at least. And you have to have the moon out of the way. But if you can make those two things happen, you'll be rewarded by seeing the pillar of light, which is the zodiacal light scattering off microscopic bits of dust in the solar system plane. I saw somebody took a picture the other day, and it was a really nice picture because the zodiacal light was like a thin pyramid of light, and it kind of petered out just about where the Pleiades are, with Mars right next to it. It was a really nice shot of all three things. Uranus is in the evening sky at magnitude 5.8. You can use the moon to find it on March 16th. In other words, find the moon on March 16th and you'll be able to find Uranus. And Neptune is really too close to the sun to be observing, and it's going to be in conjunction on March 11th. So here's what these aren't photos, by the way. This is from Sky Safari. I always share things from Sky Safari, and people think they're pictures I took. And so I guess they're pretty good images from Sky Safari. So that's what we saw on March the 3rd. Mars will be a little bit farther along tonight. And there's what the moon and Uranus will look like on the 19th in a 5-degree field, binocular field. Now we'll move along. Technically, according to the meteorologist, it is now spring as of the 1st of March. So it's time to start looking for the spring constellations. They're all pretty standard ones. I always quibble that Libra is a spring constellation. I associate it more with summer, but there you go. So Ursa Minor, Ursa Major are two of them, which are, fairly easy to find, and Boötes, Leo, Virgo, and Libra. All pretty classic constellations to look for. So if you follow that link, it'll explain all of the requirements for the Explore the Universe certificate and pin. You don't have to be a member, but what you do need is, can anybody hear that beeping? I'm just going to let it go. So in order to get your certificate, you have to observe half of all of the different things, like half of the constellations, half of the stars. There's a bunch of objectives on the moon, and you only need half of them of each of them to get your certificate. So there's lots of options. You don't have to observe everything in the list. So there's 110 total, and there's 55 sort of minimum that you need in order to get your certificate and pin. And you don't need to be a member. I already said that. So here are the stars for Explore the Universe to locate as you're going through the constellations. So a nice clear evening in the spring, you can knock off quite a few things here, both on the constellation side and the star side. So Polaris and Kochab are two of the stars. I have them ranked by brightness on the right-hand side. So starting with the sun as 0 and Sirius as 1. These are the brightest, where they fit in the brightest stars of the sky. The last 3, the nebula and 2 stars I won't even try to pronounce in Libra. They're not in the 50 list of brightest stars, but
They're easy to pronounce, Dave. Zubin El-Ganubi and Zubin Eshamali.
oh, Gesundheit. Yeah. So I think that
Just an aside.
I read some.
Dave,
Sorry.
just an aside. My doctor
Yes.
is from Libya, and I was out with him with my telescope one night describing the stars, and I talked about Zubin el-Janubi and Zubin el-Shamali, and he says, "Oh, left and right."
Yes.
He
Well,
knew exactly what I was talking about.
Well, I should have done the research on this, but at one time, Libra used to be part of Scorpius, and they were the left and right claws of Scorpius,
Exactly. Yeah.
which sounds reasonable. But then I said, well, wait a minute, it's one of the zodiac signs. So if it was part of Scorpius, so I don't know. Somehow it became its own constellation at some point. Maybe when somebody needed to have 12 to divide the sky up, they decided to break it out. I think I don't know if John McPhee is there. I think one of his email addresses has this in it.
It does.
Yeah. So in terms of deep sky for Explore the Universe, it looks pretty slim, and that's only because there's lots of deep sky objects in the spring sky. It just happens that most of them are dim galaxies for which you need a telescope. You don't need a massive telescope, but you need a telescope. And so for the Explore the Universe program, which is really meant for visual and most binoculars, you can use a telescope. But in terms of the targets for the deep sky in spring, they only have 3. The Beehive cluster, the Coma cluster, and this is the star cluster, Coma cluster, not the Coma cluster of galaxies, but they're both in Coma. And a globular cluster, M5, which I don't know if it's in Boötes or is that Serpens? One of those two anyway. Probably the easiest ones to find are the Coma cluster and M5. Beehive, the Beehive is nice, but it can be a bit underwhelming in light polluted skies because there's not a lot of bright stars in it. The Coma cluster is quite nice. But embedded in the Coma cluster is a very nice double star, which is actually in the list, 17 Coma. So it's one of the stars in the cluster. And so the challenge is to go and find that cluster and maybe observe that double star. I don't have a list of the double stars here. I kind of ran out of time, but I'll see if I can do that for next time. There's quite a few double stars. So that's it for my presentation. If anyone has any questions, I'll gladly entertain them now.
Troy has asked the question for zodiacal light. When do you look? Is it right after sunset or right after dusk ends?
No, you wouldn't see it after sunset because the sky, the twilight is too bright. So I would say you should definitely be seeing it after dusk end. But there's a kind of a transition there between, you get into twilight and then twilight fades and then there's this glow that's left over. But it looks different from twilight because it's a bit more narrow and angled along the ecliptic. So I would look at the end of dusk or maybe start looking just a little bit before if you want to sort of see it come out. But if you wouldn't see it right after right after sunset. You have to wait until the end of dusk. Good question.
Yeah, Dave, I looked at your picture of Jupiter and Mercury. I don't know, maybe it's my computer, but I can't find either one of them on the photograph.
What photograph?
The one you submitted there the other day on.
I submitted a sketch.
No, well.
And I said, here's a picture of what the sky colors looked like.
Oh,
but I said that you.
Okay, so.
Well, I said right in the caption that the planets weren't visible.
Oh, okay. Because I was looking, trying to see it when I was up, because I was at work at 5:15. So.
Yeah, well, maybe that could have something to do with it. But I was trying to be clear on that. I didn't capture them in a photograph, but I thought people would be interested in the sky colors because my drawing didn't capture the colors. It only showed you the.
Oh, I see.
Was,
okay.
It was, Got to read the fine print, buddy. Yeah, I thought that might confuse some people, but.
Okay. Any other further questions for Dave before we move on?
Okay, well, thank you.
Okay, thank you, Dave. Very informative. And if you'd like to review Dave's presentation, it is currently on our website. You can just go onto the main page and click on it, and away we go. You can review it again at your leisure. Okay, so I guess next up is me on news from the board. Halifax Center. Every month we try to present what's coming up with respect to business from the board, both here locally as well as stuff coming down from national that's exciting to hear about. If you'd like to know what's going on in our center, you can go to our website at halifax.rasc.ca. And if you'd like to contact us with any questions or suggestions, it's president@halifax.rasc.ca. Certainly our calendars, you can get yours now. You can still get them from us. You can send a $25 e-transfer to our treasurer at the email address treasurer@halifax.rasc.ca. Include in the messages field your name and mailing address so that we can then mail it off to you. There are still some editions left, so please get yours now before it's too late in the year. Our fundraising has come along great. We have a new total. It's up from last month. We now have $8,610 due to the generosity of our members in donating funds. Our Astro Images donations remain at $357.52 profit from that particular venture. In talking to Blair, I believe yesterday, we may come up with some additional photos later on in the year. So there'll be a new selection. I guess I should screen share, yes? People see that now? I hope.
You're good, yep.
Okay, sorry. I did that last month too. Not good. But in any case, as I said a moment ago, our total is up from last month to $86.10, and our profits for the Astro Images remain current at that. And we will be looking later on in the year for additional photos from our Astro Images in the imagers in the center to donate. And again, thanks to Mary Lou Whitehorn for her sketch of the center. And speaking of the center, in January, we knew that we had the mast installed along with the electrical panel. On February 15th, John Ledard, who couldn't be with us today because he is currently out at SCO, and I'll explain why in a moment, but on the 15th, he went out just to do an inspection, and lo and behold, the masthead was actually connected to the power grid. And as of this afternoon, the electrician was there, and there are now lights as of 2:20 this afternoon. There's both red and white lights inside the warm room now. And as well, the observatory is connected to the power grid. So we have electrical at SCO as of this afternoon. So yay, we're getting there. Observing certificates. Congratulations to Lisa Fanning for her second certificate since she joined just this past summer. So congratulations, Lisa, on Explore the Moon Certificate Telescope Edition. I was privy to your certificate. It is being mailed to you, dear, from the national office, but congratulations on your second. And speaking of Lisa, who is one of the co-editors along with John McPhee on Nova Notes, The newest edition of Nova Notes has been mailed out to those who paid for that service, and it is currently on our website as well for those who would like to go read it. The announcement went out earlier this week. So thank you again, Lisa and John. It's a phenomenal issue. You can see from the cover that it has a different look. There are 3 different segments that they have divided it into, which is from the editor, with section 1, which is background sort of information about the center, Members Universe, which are photos and articles submitted by members, as well as a section regarding the business of the center. So thank you again to Lisa and John. And we always like to focus on our center stars. These are people who have been published in one of the RASC publications or further afield, or have been acknowledged for something astronomical. And this month it's Dave Chapman is our member, along with Kathy LeBlanc, who in Sky News, the latest edition of Sky News, have an article written by the editor of the magazine about two-eyed seeing. So congratulations, Dave, on that really nice article. And as you heard earlier, congratulations to Blair McDonald for his service award, as well as to James Edgar, one of our newest members, at least to us, for his Fellow of the RASC award. Oop. Sorry about that. Let's go back. Unistellar Optics contacted us over the past month, and actually the past week, and advised us of something they have called the Messier Marathon Week. It's March 10 to 16, which is coming up. It's a marathon that they have that you can join one of many different what they call races. Keeping in mind that Halifax Center is not organizing a marathon event related to this, but we are inviting our members who are interested in doing something like this to please do so. You can go to their website, which is the unistellaroptics.com/Messier, and you can find out about all sorts of stuff about the different races. If you want to actually register, what they're trying to do is get the largest number of people involved in this Messier Marathon worldwide, not just here in Canada, but across the world. So it's really exciting for those that are interested in that sort of thing. There's a free ebook which explains all the different races and about the Messier objects that you need to observe. You can share observations also for other things. And here's a list of some of the races. There's the Messier Marathon, which is the full 110, the half marathon, obviously the 55. There's a relay where you can have 2 or more individuals involved and both participating and finding the Messier objects at different times so that you're combining your efforts to get the 110. There's Messier in the morning, which you can get as many objects as you can starting at 4 a.m. Or if you're a night hawk or an earlier evening person, it's till midnight, which is 8 p.m. to midnight. And there's 3 sprints that you can also participate in. One is a galaxy, one is the nebula, and one is the star cluster. So you can choose which one there. And please note that I must make this disclaimer, that RASC Halifax Center does not necessarily endorse the products or services of Unistellar and takes no responsibility for the performance of either the vendor or their product and or services. This is totally something that's outside of our organization, but thought you might have an interest in knowing about. So joining RASC, one of the things about joining RASC, and unfortunately I did not do this at the beginning of the presentation, but there are certain perks of joining RASC. One is the Observer's Handbook that you automatically get as part of your membership every year. And as we mentioned earlier, James Edgar is our editor for the Observer's Handbook. You can also get copies of the Explore the Universe Guide, which is a program that anyone, not only members, can participate in, but members do get the actual guide. And you can certainly purchase the workbook that goes along with it that allows you to enter all your observations in it and send in as a means of acquiring your certificate. The Journal of the RASC is also one of the perks. There are several very interesting articles and photographs that come into it every month or every issue. The Sky News, as I mentioned earlier, this month's issue has the article with Dave and Kathy in it, but there are lots of other really cool things that focus on Canadians and what we do here in Canada. And I believe Michael Gatto mentioned about lens or mirror developers. There's an article in here about the modern makers of mirrors, so you might find that interesting there as well. And certainly you have access to all sorts of RASC events. Here locally, you have access to our newsletter, our observatory at St. Croix, as well as to other information that comes down through the membership. So how do you join? Well, you can join online, which is really easy. If you go to our website and you go to the item called About Us and the menu items, you'll find this column, and if you click on the word join, that'll take you to the national website and you can join online. However, if you're old school and prefer to do everything in paper, you can certainly click on the word form, and that'll bring you to the PDF of the form that you can print off and mail in along with your payment. And as I mentioned, or I didn't mention, but if some members, because of the COVID-19 challenges, may require some assistance in paying for their membership, if that is the situation with you, please contact Adela Ziffi at mempub@rasc.ca and inquire there, and she'll be able to assist you there. Halifax Center perks, well, we have an email discussion list that you can list. And keep in mind, there is one as well for the national, and both discussion lists are optional. You are not automatically given access to them. You do have to register for those discussion lists. And certainly our members have access to the St. Croix Observatory. With the National RASC, all sorts of neat, wonderful things going on with the online activities. If you go to their National RASC website, you can see all the activities there on their site. Some of the speakers that are coming up are really quite intriguing. On tonight, for instance, it's at 8 o'clock Atlantic, Eastern, 7 p.m. Eastern, for those of you outside the Atlantic region. The Dunlop Observatory Astronomy Night has a speaker addressing the life cycle of massive stars. On March the 12th, that you can see there, the Native Skywatchers are presenting Two-Eyed Seeing, Hawaiian Indigenous Astronomy and NASA Moon to Mars. On the 17th, there's the RASC Toronto Centre Speakers Night, and professor from the University of Victoria is going to be addressing exoplanets. And on the 18th, RASC Calgary, which means it'll be a late night for us here on the East Coast. It'll start at 10:30 our time. He'll be addressing neutron stars, supermassive black holes, and supernova remnants. So something, if you're interested in any of those, you can do so. Star parties are listed, speaker series, Explore the Universe. These are the pre-recorded sessions with Jenna Hines and our very own John Reed. They will be beginning again on June 25th. And I guess I should have mentioned right off the top, what's really cool is that starting April 1st, the Moon at Noon, which will allow members to go through the Explore the Moon certificate program, it'll begin at 12:30 Eastern or 1:30 our time. So if those that are interested, please participate in that as well.
Judy.
Insider's Guide to the Galaxy continues on Tuesdays. For
Judy.
our own center, heads up for the meetings. Our next meeting is April 10. It would have been April 3rd, the first Saturday. However, that's Easter weekend, so it's moved to April 10. Our speaker for that session, main speaker, will be Adam Gonzalez. He's a PhD student at SMU, works with Dr. Gallo.
Dave wanted to ask a question.
Sorry, Dave, my apologies.
No worries. I just wanted to mention that I'm giving I'm the guest speaker at the Kingston Center meeting. I'm surprised it's not on that calendar, but it's this coming Wednesday night at 8 p.m. our time. The information on if it's open to anyone. If you go to the Kingston Center website, kingston.rasc.ca, you should be able to go. It's about the mini robotic observatory, which I know some of you have seen some of the images that I've taken from this little tiny telescope in my backyard. So I'll be giving a talk there, and then also I'm going to repeat it again in May to the Winnipeg Center as well for the late night crowd.
Great, thanks, Dave. That's great. On April 10, Dave Chapman will also be speaking about the RASC double stars. So I'm assuming, Dave, you'll be able to address that, what you were talking about earlier in your presentation at that point. On May 1st.
Sure thing.
Sorry?
I said sure thing.
May 1st, we can welcome Chris Gaynor, former president of RASC, and he's from the RASC Victoria Center. He's going to address the amateur use of the HST, and Tony Schelling will be addressing sketching lunar craters. So we'll see a different perspective on how to do sketching. June 5th, Leslie Sage. He's from Nature Magazine's Astronomy magazine, and he's the editor of it. And come fall, although we are planning to have Nova, well, we hope to have Nova East, but the board will determine in April and May whether or not it goes forward as a in-person or another form of the event. We'll have to wait and see how things are progressing here in the province. September 11th, which is again the second Saturday, keep in mind Labor Day is September 6th. Our speaker is David Hoskin. He's going to address Comet Neowise. The board is working on speakers for October 2nd and 6th, and I think if it works out really well, you're going to be really excited about who we're getting for this. We'll keep you on tenterhooks until then. And December 4th at our AGM, Dr. Phil Groff, who's the RASC Executive Director, has agreed to be our speaker to address what's happened at RASC over the past year and where is it going in 2022. So, questions? Okay, given there aren't any, that is actually the end of our official meeting. So thank you everyone for attending. I hope you found this informative and there's a piece of something new that you learned. At this point, we are going to stop recording, and those that wish to remain online can do so and join us in our Astro Chat. So until we meet again on April 10th, stay well, keep looking up. We'll see you next month.